En Fundación UNAM seguimos trabajando por la cultura, la ciencia y la educación. Sin salir de casa, reflexionarás con los martes de ciencia, a través de las conferencias Universidades por la Ciencia, que emitimos en conjunto con el Colegio Nacional. Y para disfrutar, regresamos con la segunda edición de los ciclos de documentales de Jueves de Ciencia, con la transmisión especial de TV UNAM. Además, conversamos sobre nuestra nueva realidad y sus afectaciones en distintas disciplinas a través del Corredor Cultural de Autonomía. Sigue nuestras redes sociales y no te pierdas ningún detalle en www.fundacionunam.org.mx.
Se han efectuado varias estimaciones de cuántos hongos existen en la naturaleza, y es un dato difícil de precisar. Se ha calculado 1.500.000 especies, de las cuales conocemos hasta ahora alrededor de 90.000. Ni animales ni vegetales, los hongos son tan excepcionales que pertenecen a un reino diferente.
En Fundación UNAM seguimos trabajando por la cultura, la ciencia y la educación. Sin salir de casa, reflexionarás con los martes de ciencia, a través de las conferencias Universidades por la Ciencia, que emitimos en conjunto con el Colegio Nacional. Y para disfrutar, regresamos con la segunda edición de los ciclos de documentales de Jueves de Ciencia, con la transmisión especial de TV UNAM. Además, conversamos sobre nuestra nueva realidad y sus afectaciones en distintas disciplinas a través del Corredor Cultural de Autonomía. Sigue nuestras redes sociales y no te pierdas ningún detalle en www.fundacionunam.org.mx.
Se han efectuado varias estimaciones de cuántos hongos existen en la naturaleza, y es un dato difícil de precisar. Se ha calculado 1.500.000.
Bienvenidos a el ciclo de conferencias de Universidades por la Ciencia, organizado por Fundación UNAM y un conjunto de universidades y centros de investigación en México, Estados Unidos, Reino Unido, España, Brasil, y les agradecemos mucho el que nos acompañe. El día de hoy tenemos una conferencia muy especial a cargo del doctor William Phillips, recibió el premio y es investigador en el Instituto Nacional de Estándares y Tecnología en Estados Unidos y en la Universidad de Maryland en el Quantum Joint Institute. Es realmente un honor tener al doctor Phillips, quien es además una persona muy cercana a nuestro país, a México. Es miembro de la Academia Mexicana de Ciencias, de lo cual estamos muy orgullosos, y ha tenido un número muy grande de estudiantes, de profesores de México trabajando con él, incluyendo grandes amigos como Luis Orozco. El día de hoy la conferencia es sobre un tema muy especial que vamos a comentar en un momento. Y welcome to the University for Science seminar series organized by the UNAM Foundation and the International Consortium of Universities and Research Centers. Today, we have a very special conference by Dr. William Phillips, who is at the National Institute of Standards and Technology and in the Joint Quantum Institute of the University of Maryland. Thanks, Dr. Phillips, for accepting the invitation, and it is a great honor having you here. We are joined by the president of the UNAM Foundation, Dionisio Meade, the executive director of the UNAM Foundation, Araceli Rodríguez, the coordinator of the physical and engineering sciences area in the university, in the UNAM, Demetrio García Nochetti, and Araxi, Dr. Araxi Urrutia, who is the coordinator of and the originator of the University for Science Consortium. Thanks very much to all of you for attending us. And Dr. Phillips is a prize in physics at a very early age, long time ago, in 1997, for his research and the development of the laser cooling and trapping of atoms. It's an amazing contribution, an amazing development that has a boundless possibilities for atomic physics. And the impact his development has marks one of these unique moments in science before and after a scientific discovery. And developing this method for cooling and trapping of atoms has a lot of challenges, including instrumental ones. And Dr. Phillips was uniquely positioned to do this work. He made his doctoral research in the Massachusetts Institute of Technology, measuring the magnetic moment of a proton in water, which still remains one of these unique experiments in science. Dr. Phillips today will talk about the new measurement, the quantum reform of the metric system. And we will see that this is one of these new developments that is changing everything, and gets together the technology and the science together. And Dr. Phillips is a very close friend to Mexico. He has a lot of students and research colleagues, including very good friends, and he's a fellow of the Mexican Academy of Sciences. I think I already mentioned it, and we are proud because of this. So thanks very much. And las preguntas van a ser coordinadas por la doctora Urrutia y podemos recibirlas en todas las plataformas en cualquier momento. El doctor Phillips es generoso con algo que él ha mostrado que es una de las características más valiosas en el universo, que es el tiempo, que por otro lado permanece como una pregunta abierta. Y doctor Phillips hace con lo más precioso que se tiene, lo comparte con los que él quiere. Dr. Phillips is very generous with one of the most precious items we have in the university, and it's time. The research by William has shown that time is one of the fundamental open questions still remaining, and understanding time is one of the great challenges we have. And Dr. Phillips does with the most precious thing, time, sharing with the dearest and loved ones. So we are particularly grateful that today he will share his time, his extremely valuable time with all of us. Agradecemos al Dr. Phillips que comparta el tiempo, que es algo muy valioso, lo comparta con nosotros y de una manera muy generosa. Le paso la palabra con mucho gusto a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade. And thanks, Philip. Thanks, Bill.
Muchas gracias nuevamente al doctor William Phillips por acompañarnos. Para nosotros que esté presente en este consorcio es un motivo de estímulo, un motivo de orgullo y una muestra del potencial que puede tener este vínculo entre universidades cuando gentes de la capacidad, de la preeminencia y de reconocimiento del doctor Phillips nos acompañan en nuestras reuniones. Muchísimas gracias de veras, es un orgullo y yo creo que acrecienta las posibilidades que nosotros hemos concebido de la nueva realidad después de la pandemia. Esta nueva realidad implica el aprovechamiento de las plataformas, implica el vínculo entre académicos, implica el vínculo entre los científicos e implica sobre todo la posibilidad de que muchos jóvenes accedan al mundo del conocimiento y encuentren en este mundo la posibilidad de realizar sus capacidades profesionales. Nosotros estamos muy claros de que la nueva realidad que emana después de la pandemia implica, desde luego, reconocer que la ciencia importa. Yo creo que esa es una de las lecciones fundamentales y yo creo que se ha revalorado el cuidado del planeta y se ha revalorado el conocimiento científico como instrumentos esenciales para poder superar en el futuro los retos y los desafíos que se nos presentan. Para nosotros, además, es una gran oportunidad que se nos compartan investigaciones en curso. Esa es precisamente la característica de las pláticas que cada martes tenemos y eso es lo que nos hace sentir también muy motivados de poder compartir este conocimiento con gentes de la talla, del conocimiento, del prestigio del doctor William Phillips, un premio Nobel que hoy nos acompaña. Agradecemos de veras al Colegio Nacional, agradecemos a la UNAM, agradecemos al doctor Demetrio Fabián García que hoy nos acompaña, agradecemos a Araxi por haber impulsado esta iniciativa, pero yo creo que todos debemos de reconocer que fue un acierto, que en medio de las adversidades de la pandemia, encontrar estas posibilidades de comunicación con el mundo científico, tener la posibilidad de compartir el conocimiento y poderlo hacer sin límite de fronteras, con independencia de horarios, con la suma de muchas universidades que se han sumado al consorcio, genera un potencial formidable que apenas está bosquejando las posibilidades que tendremos en el futuro de intercambiar información y de estimular el conocimiento. Gracias de nuevo a todos por acompañarnos. Es motivo de particular orgullo darle la bienvenida al doctor Phillips y agradecerle además que comparta su tiempo, pero que comparta también su afecto por México. Muchos mexicanos se han formado bajo su protección, bajo su tutela científica y para nosotros eso es un motivo también de reconocimiento porque hay más y más científicos mexicanos que están encontrando en la ciencia el camino de su desarrollo. Gracias de nuevo, sean todos bienvenidos y listos para escuchar la presentación del doctor William Phillips. Muy buenas tardes.
Muchas gracias y le pasamos la palabra al doctor García Nochetti si quiere comentar.
Thank you very much.
Yes, thank you very much. Thank you very much. It's a pleasure to be here. And also, I just want to tell you, as a coordinator of this area, which is mathematical and physics and engineering science, we actually do a lot of, we invite a lot of our professors and students to follow the conference because the subject is very interesting, and also the idea of all the instrumentation is the area of great interest of several groups in this council. We are very pleased to be here, and a lot of people is actually following your conference. Thank you very much.
And thanks, and Bill, please.
Well, thank you very much for all of those kind remarks and the kind welcome. It's a pleasure for me to be here with you, and I'm very pleased to be able to tell you about this topic, which I've called a new measure, the quantum reform of the metric system. And as you've heard, I'm from a place called the Joint Quantum Institute, which is joint between the National Institute of Standards and Technology and the University of Maryland. And NIST is the National Metrology Institute of the United States. And there I'm part of the Laser Cooling and Trapping Group, which is led by Gretchen Campbell and also includes Paulette, Trey Porto, Ian Spillman, Ida Tietzinger, and Charles Clark. And this talk is also under the auspices of the International Union of Pure and Applied Physics, which has been one of the strong supporters of the International System of Units since its beginning. And as a member of one of its commissions, I am helping to spread the word about the new quantum reform of the International System of Units. So, what is the nature of this reform of the International System of Units? Well, the metric system, the informal name of the International System of Units, came to us as part of the French Revolution. This was perhaps the biggest revolution in measurement that there was. This painting by Delacroix evokes the kind of a revolutionary spirit that changed the way in which the world measured things, as well as many other things as well. And today, my claim is that we are experiencing the biggest revolution in metrology since the French Revolution. And the nature of that revolution is a change in the definition of the base units of the International System of Units. 7 units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, are the basis of all other measurements. And the nature of the revolution is that today, every one of those units is defined by fixing a value of a constant of nature. Now, in order to understand how that is even possible, that we can define a unit by fixing the value of a constant of nature, how it's possible to fix a value of a constant of nature, I'd like to, with apologies to the late great Stephen Hawking, to give you my version of a short history of length, rather than a short history of time. Since ancient times, the standard of length has been based on the human body. A foot was a foot. A fathom was the distance of the wingspan of one's arms. A cubit was the distance between the elbow and the fingertip. Well, this was extremely convenient and really important to have such measurements because of commerce. In fact, a history written based on the description of one of the early conquistadors, Cortez, indicated that in Mesoamerica, pre-Columbian Mesoamerica, that units of measure were abundant and that people had units of measure for everything. Here in this wonderful mural, we see some units of volume being used in an active marketplace. One of the traditional units of length, the distance between the navel and the ground of a person, is very close to our modern definition of a meter. So, as I said, all this was very convenient because you had the standards of measurement with you all the time but it wasn't very consistent. If you were buying, for example, fabric from a short fabric merchant, then you might get less fabric than you had expected. And so all ancient societies faced this problem of the inconsistency of basing units of length on the human body. And so one approach was to base the unit of length on a particular human body. In the case of the ancient Egyptians, that was the pharaoh. So the length of the pharaoh's forearm became the royal cubit of ancient Egypt, and this was at least consistent, but it was no longer as convenient as using whatever body was at hand. And so the ancient Egyptians did something that was remarkably modern. They made an artifact. They took the length of the pharaoh's arm and they embodied that length into a stone that was the length of the pharaoh's forearm. And this stone became the standard of measurement for ancient Egypt. People doing things like building the pyramids out in the field used secondary standards made out of wood, and they had to recalibrate them every month. And the rule was that the penalty for failing to recalibrate was the death penalty. These people were really serious about metrology, and the result was that they built things extremely well. The baselines of the pyramids are consistent to a fraction of a percent. They're square to 12 arc seconds. They're really extremely well made because of the seriousness of the metrology. Well, this idea of having an artifact, an object that sets the standard of length, is something that was adopted all over the world. In Europe, for example, it was common for such artifacts to be built into the wall of the town square. And here in the city of Regensburg, in the region of Bavaria in Germany, we see one of these standards of length. This is the standard fathom for Regensburg. And as you can see, it's quite a good size fathom. So this might be an exceptionally fine place to buy fabric because you would get a lot of fabric for the measure of a fathom. But the problem was that if you went to one of the surrounding towns in Bavaria, you would have a different standard of length. Well, this was a problem that was deeply annoying and extremely common throughout Europe. And so it was the French revolutionaries who decided that they needed to solve this problem once and for all. And in the revolutionary spirit of universality, the spirit, the motto of the French Revolution was equality, fraternity, liberty. And so in that spirit, they decided that they should have a standard of length that was available to all people. And so they decided to define a new unit of length called the meter. And the meter was to be 1/10,000,000th of the length between the North Pole and the equator on a meridian going through Paris. And so in order to realize this new unit, this new definition of a unit of length, and when I say realize, I mean to bring into reality this unit, they sent out surveyors north and south from Paris to go to Barcelona in the south and to Dunkirk in the north to measure the length of the meridian along that segment, and then they extrapolated for the rest of the quadrant of the Earth to determine what the length of a meter was. They came back from this expedition, which took them several years and was extremely dangerous because there was a war going on. And they reported their results in units of the old standards of measurement that had been in use in Paris at the time. The feeling was that they had brought, not just to France, but to the world, a system of measurement, or at least a unit of length, that would be good for all times, for all people. à tous les temps, à tous les peuples. And in this medal that was cast in order to commemorate this event, you see a sort of mythological creature measuring the earth, which is indeed exactly what they did. They measured the earth. And that measurement was, as I said, brought back to Paris. And they did the same thing that the pharaohs did, that the ancient Egyptians did. They made an artifact because, of course, it wasn't convenient to continually be doing surveying to determine the length of the meter. What they wanted was a standard. And so they made this platinum bar 1 meter long from end to end and deposited in the archives of France. And it is known as the meter of the archives, deposited there in the year 1799. So we see that either the Egyptians were being extremely modern or the French revolutionaries were borrowing a very ancient idea, an artifact that determined the unit of length. Well, excuse me, some few decades later, the entire world agreed to adopt the metric system. And in the famous 1875 Treaty of the Meter, the Convention du Mètre, the countries around the world agreed that they would adopt the meter as their standard of length. And it was also agreed that they would make a new standard of length. This one, a bar that you can see here, made of platinum iridium, where the standard is that the distance between two scratches on this bar is 1 meter. This was preferable to the old N standard, because the problem with an N standard is that in order to determine the length, you need to touch the ends. And that, of course, has the disadvantage that it may wear them down. Here, one could use a microscope to look at the scratch and then translate the microscope using a precision screw drive. And this is the way in which meters could be compared and standards of length could be maintained. So this was the standard of length, the international prototype of the meter, kept in a vault in a town outside of Paris. This was the standard of length for the entire world as of 1875. Well, it was made a few years later. That was the standard of length for the entire world. The problem was that almost as soon as they made this new standard of length, people realized that there were better ways of measuring length. The distance between two scratches, even when you're using a powerful microscope to look at those scratches, is not a very easy definition to use. Where is the middle of the scratch? It's a scratch, after all. It's not a very well-defined object. What I'm showing here in this picture is a cartoon of a device known as an interferometer. In the 19th century, people discovered that light was a wave. Newton had thought that light was a stream of particles, but in the 19th century, it was discovered that light was a wave. It was discovered that it was a wave of electric and magnetic fields, and because it's a wave, it means that different beams of light can interfere with each other, and they can interfere constructively when the waves line up to make a brighter light, or it can interfere destructively when the waves cancel each other out to make darkness. And this device, known as an interferometer, can do that, and it can measure length. It works like this. Light comes in and bounces off a beam splitter, a half-silvered mirror that reflects some of the light, so that some of the light will come in and be reflected and sent to this mirror, and some of the light will be transmitted and sent to this mirror. Each of these mirrors reflects the light back, and again, some of the light is reflected toward this screen, and some of the light from this mirror is transmitted toward this screen, and those two beams of light interfere so that in some places they make a dark spot, and in other places they make a bright region. But here's the point. If this movable mirror is moved 1/4 of a wavelength of light, this means a small fraction of 1/1,000,000th of a meter, then we will change this pattern from being dark to being light. And that makes it easy to measure lengths that are even smaller than that. So it became easy to measure lengths that were smaller, that is, to measure lengths with a precision that was better than a small fraction of a millionth of a meter. And that was not something that you could do by looking at a scratch on a bar of metal. And so, for a long time, people used the wavelength of light as a kind of de facto standard. It was not the official definition of length, but it was the definition of length that everyone used because you could make measurements using that definition much better than you could using the international prototype of the meter. Finally, in 1960, which was the year that the laser was invented, the meter was redefined. It was redefined to be a certain number of wavelengths of light from a krypton lamp. You put krypton gas in here, you run an electric current through this this gas-containing bulb, and it produces light, an orange light, and the new definition of the meter said that the wavelength of that light was a certain number of meters, and that became the new definition of the meter. But almost as soon as this definition had been made, so that we now had a definition for the meter based on the wavelength of light, it was found that the light coming from this lamp was not perfectly pure, that the light from a laser was far more pure, that the light coming from this lamp was a mixture of colors, whereas the light from a laser was a much more pure single color. And so people started to use devices like this. This is a helium neon laser that produces a red light, and its wavelength is locked to a transition in molecular iodine. So this so-called iodine-stabilized helium neon laser became, again, an unofficial standard of length. People started to use this as their de facto standard of length. Again, as in the previous case, it was not officially in legal meters, in SI meters, but it was the length standard that everyone used because you could make such better measurements, much better measurements, using laser light. And so, again, we faced the situation where the meter needed to be redefined because you had a technology, lasers and laser interferometry, that was much better than the old technology of using a krypton lamp and doing interferometry with the light from that krypton lamp. So the obvious choice, if we'd followed the tradition of the past, would have been to redefine the meter in terms of the wavelength of the light coming from an iodine-stabilized helium neon laser. Fortunately, the people at the time did not do the obvious thing. They did something far more brilliant, far more beautiful. What they did was to define the speed of light. What does that mean? The new definition of the meter is that the meter is the length of path traveled by light in vacuum during a certain time interval. If you say how far light travels in a certain length of time is the definition of the meter, you have effectively defined the speed of light in the process of defining what you mean by a meter. So when you say that the speed of light is a certain number of meters per second, that's a way of defining what you mean by a meter. This equation, that the wavelength of light times its frequency is equal to the speed of light, is universal. It doesn't matter what the wavelength of light is, this expression is still true. So what it means is that if you measure the frequency of the light, and this is something that by 1983 people had learned how to do, if you can measure the frequency of the light, and if you define what the speed of light is, you immediately know what the wavelength of that light is. So you see the beauty of this? If someone makes a better laser that is more pure, if someone devises new techniques for measuring the frequency of light, and people did both of those things, this expression is still true, and that better laser, that better technique for measuring frequency, can be used to realize the meter without changing the definition. The improvement in the ability to know what a meter is automatically included in this expression. This is the thing that is so beautiful about it. So here is one of the key things to understand about what happened with length. We started with an artifact. The length of a meter was the distance between two scratches on one of these bars. We realized that wasn't so good. We had a better technology, namely interferometry with light coming from a lamp. And so we defined the meter in terms of an atomic property, a quantum property, the wavelength of light coming from a particular atom, in this case, krypton. But then, when that particular atom was not the best atom you could choose, then the final step was to define the length not in terms of a particular atom, but by defining a universal and fundamental constant of nature, namely the speed of light. And the beauty is we will never need to change the definition again. What a beautiful and brilliant definition. What I'm here to tell you about is that just 2 years ago, the international community brought this same beauty to a redefinition of the kilogram, and for that matter, to a redefinition of the ampere, the Kelvin, and the mole. Why was it necessary to do that now, and how was it done? In order to understand that, I'd like to bring you a light history of mass. Here is a picture of a number of standard stones, artifacts that were used as mass standards in ancient Babylonia. These mass standards had the same problem that all other artifact standards have, that they may vary from place to place. Somebody else has a different set of artifact standards. And so the universality of a definition of mass is lacking. What was the definition of mass in Babylonia? You had a different definition of mass in Europe, a different definition of mass in the Americas. The French revolutionaries decided to attack this problem in the same way that they had attacked the problem of length. They would define a new unit of mass, which they called a kilogram, in terms of something universal, the volume of 1 cubic decimeter of water. That is the mass of a volume of water of 1 cubic decimeter, or 1 liter, as we say. This is beautiful because it relied on the meter, this new universal length standard, and it relied on water, something that was readily available to everybody. The trouble was that it wasn't so easy to use. The density of water changes with temperature. There's buoyancy that changes with changes in air pressure and temperature. And so it was very hard to have a consistent definition of mass based on water. And so they did what metrologists have done so many times in history. They made a new artifact. And here is that artifact. I'm holding not the artifact itself, but the box in which it is held. This is the kilogram of the archives. In 1799, this platinum cylinder, made to be as close as possible to the mass of 1 liter of water, was deposited in the archives of France and became the unit of mass for the nation. A few decades later, at the International Treaty of the Meter, the Conferencia de Metre, the countries of the world agreed to adopt the kilogram as the universal standard of mass, and they agreed to create a new international prototype of the kilogram, made to be as close as possible to the mass of the kilogram of the archives. And this is a picture of that international prototype of the kilogram, held under 3 jars of glass to keep it clean. This was, until 2 years ago, the artifact standard of mass for the entire world. And it was the last artifact. This is the definition. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. A simple definition, but think about this. We are in the 21st century. The unit of mass for the people of the 21st century is an object that was made in the 19th century based on another object that was made in the 18th century. This is a true scandal. Think about it. If someone were to leave a fingerprint on the international prototype of the kilogram, all of us would lose weight. This is an intolerable situation. And while nobody leaves fingerprints on the international prototype of the kilogram, it appears that its mass is changing nevertheless. Here is a plot of the mass of a number of copies of the international prototype of the kilogram. These copies were made at the same time as the international prototype, made to be as identical as they can be to one another and to the international prototype of the kilogram. The IPK, as we say, was chosen because its mass was the closest to the mass of the kilogram of the archives. All the others were a little bit different, and those differences were cataloged and subtracted out, so that at the beginning, when all of these copies were made, we knew what a kilogram was in terms of all these copies. But as time went on, the mass of those other objects changed. Every few decades, these objects would come back to Paris and be compared against the international prototype of the kilogram, and they did not stay constant. Now, when you look at this graph, you see that almost all of those copies of the kilogram are increasing in mass. Now, this makes you think that what's really happening is that the international prototype of the kilogram is losing mass. The trouble is that it cannot. By definition, the international prototype of the kilogram always is exactly 1 kilogram. But, of course, that's not what's really happening. But what does the word really even mean in this context when you have defined the unit of mass to be based on an artifact, this piece of metal that is sitting under those bell jars? What can you do? We had to solve this problem. We had to solve this scandalous situation where apparently the very standard of mass itself is something that is changing in time. How did we solve this problem for the meter? We defined the speed of light. We want to use that same beautiful idea for a redefinition of the kilogram. We want to define the value, to fix the value of a constant of nature, a universal constant. What constant do we use? Well, to understand that, I want to ask you to recall what is probably the most famous equation in all of history, that the energy, E, of an object at rest is equal to its mass, m, times the speed of light squared. E equals mc squared, almost certainly the most famous equation in history. We have another equation for a different kind of energy. This is Planck's equation. The energy of a photon, well, he didn't use that term, but we now call a particle of light a photon. Its energy is equal to Planck's constant times the frequency of the light. Remember, light is a wave. It has a frequency at which the electric and magnetic fields wave back and forth. That frequency times Planck's constant is equal to the energy. Now, what I'm going to do is take those two equations and set them equal to each other, because they are both equations for the energy, and solve the mass. So the result is that the mass is equal to Planck's constant times the frequency divided by the square of the speed of light. What does this mean? If you had an object, a particle, let's say a nucleus, and the nucleus radiates a photon, a gamma ray. So we might imagine any number of radioactive nuclei that give off gamma rays. The change in mass of the nucleus after it gives off a gamma ray that has a frequency f is equal to Planck's constant h divided by the square of the speed of light. Now, this isn't the way we're going to do our new mass measurements. We're not going to weigh photons. In principle, we could. In fact, we do weigh photons, but not well enough to serve as a mass standard. This is where this wonderful genius Brian Kibble comes in. What Kibble said was, let's imagine an electromechanical device. We now know it as a Kibble balance or a Watt balance. And let's use it along with a definition of Planck's constant to define the kilogram. So here's how it works. In this movie, I'm going to illustrate how the Kibble balance works. So first, I'd like you to remember how we measure mass traditionally. When we want to measure an unknown mass on this side of a balance, the way we measure it is we put known masses on the other side of the balance, and we keep putting masses on the other side of the balance, known masses, until the balance balances. And when it balances, then we know that the unknown mass is equal to the sum of these known masses. This is the traditional way of weighing things. Now I want you to imagine a different way of weighing things, one that uses electromagnetism. So imagine that on the other side of the balance from the unknown mass, which produces a gravitational force, we have a device that can produce an electromagnetic force. This device has a coil of wire in which we're going to put current. It has some magnets that create a magnetic field. And here's the current going through this coil. Here's the magnetic field. And the point is, if we know what this current is, if we know where the current goes in all the wires of this coil, if we know the strength of this magnetic field, and we know the direction in which that magnetic point, the magnetic field points at each one of these wires, then we can calculate what the electromagnetic force is. We then will know, once it balances, that it's equal to the gravitational force, and by knowing the acceleration of gravity, we can determine what the mass is. The problem is this: we do not know any of these things well enough. We don't know where the current goes in this coil. We don't know what the magnetic field is or what direction it's pointing in. And so while we can imagine this way of doing things, we can't really use it as a way of measuring mass, as a different way of measuring mass. Here's where Kibble comes in. He says, yes, we can't measure these things, but we can measure something else. What Kibble said was, take this coil that we're putting current through, and take the leads of that coil, and don't put current through, but connect those leads to a voltmeter. Now, let's move this coil up and down and measure its velocity. We call this the velocity mode of the experiment. We're going to move it and measure its velocity. And when it moves, it's going to generate a voltage. And so we see that when we move this coil at a velocity that we're going to measure very carefully, it generates a voltage, and we're going to measure that voltage very carefully. And what Kibble understood, and I'm going to show you how it works out in just a moment, he understood that if you made this measurement, all those things that you didn't know about the magnetic field and the direction in which it points and where the current goes in the wire, all of those things would be incorporated into this measurement of the voltage and the velocity. And then you could use this new idea, as it turned out, to measure mass. So let's see how that works. The idea is that the mass that we're trying to measure times the acceleration of gravity, which gives us the force that is on the one side of the balance. If we take that and multiply by the velocity that we measure in the velocity mode, that has got to equal the current that we used to balance the gravitational force in the weighing mode times the voltage generated from the velocity mode. So look at this equation. We've got on each side of the equation something that came from the weighing mode and something that came from the velocity mode. And these two quantities have to be equal because mechanical power has to equal electrical power in a proper system of units. And force times velocity is mechanical power, while current times voltage is electrical power. And so we take this equation, we solve for the mass, and find that the mass is equal to the current times the voltage divided by the acceleration of gravity and the velocity. Now you might say, but wait a minute, it seems like a good way of measuring mass, but you promised that this was going to involve Planck's constant. How does it? And the answer is that when we measure these electrical quantities, the current and the voltage, there is a quantum way of doing that using the quantum Hall effect and the Josephson effect. And if we didn't do that, if we instead used the old way of defining the ampere, this would not work at all, because on this side of the equation, we would have something that involved the mass itself. And so this would not be a good way of redefining mass. But because we're going to use a different way of making the electrical measurements, this is going to work. And that different way is the one that involves the Josephson effect. Here's Brian Josephson, and the quantum Hall effect, discovered by Klaus von Klitzing, and here's von Klitzing. What Josephson told us was that if you have two superconducting materials and you put them close to each other with an insulating layer between and put a voltage across them, there will be a current flowing at a certain frequency. And the frequency divided by the voltage will be given by this fundamental constant of nature, 2e/h, where the 2 comes from the fact that in superconductors, the electrons are paired and work together. So E/h, the charge of the electron, Planck's constant. Here's where Planck's constant is coming in, you see. What von Klitzing discovered was that if you have a certain two-dimensional semiconductor and you put current in one direction, it'll generate a voltage in the other direction, and the ratio of that voltage to the current has the unit of ohms, and the value of that resistance is quantized in units of h/e², h being Planck's constant, the thing we're trying to get, and e, of course, being the charge on the electron. And so, when you measure the voltage, you do it using Josephson effect, and then the voltage is proportional to h/2e. When you measure the current, you do it by putting it the current through a resistor calibrated using the von Klitzing effect, so the resistance is in terms of h/e², and then you measure the voltage across that resistance, which again is measured in units of h/2e, and you see that the h's cancel out of this current measurement, so the current's proportional to E. You multiply that times V, which is proportional to h/2e, and it's proportional to h. So that's how we get mass proportional to h. I realize the algebra may have been a little bit fast, so you can ask me about it in the questions if you're interested. Okay, so using this idea, people around the world, including my colleagues at NIST, have made devices that do this. Here's a picture of one of the devices at NIST that does it. And with this device, we can realize the kilogram. That is, we can determine the mass of an object in absolute kilograms, 2 × 10⁸, and that is better than the changes that we're seeing happen to the kilogram due to, well, we don't really know what those changes are due to. Because we don't have a solid standard of mass, something that we know doesn't change, but now we do. And so I'm just calling it dirt, but maybe in the future we'll figure out what it is now that we have a way of determining mass, a way that doesn't change because it's not based on an artifact. Well, here is a picture of part of the team that did this measurement to determine the kilogram. And these people, just like the ancient Egyptians, are really serious about metrology, because you see they have tattooed the value of the fundamental constants that are used to define the kilogram and the other standards of measurement. They've tattooed these things onto their forearms. Now, it turns out that there is still another way of measuring a kilogram when you've fixed the value of h. And that has to do with a very different way of doing it, where you take a single atom. Well, you take a gas of atoms, but you're considering them singly, and imagine that the atom is at rest and the atom is in its ground electronic state, but it absorbs a photon. In the process of absorbing the photon, it goes to the excited state because of the energy of the photon, but it also recoils. That is, it starts moving because it absorbs the momentum of the photon. And when you put in these numbers for the momentum of the photon and the mass of the atom, you find that the velocity by which this atom recoils is Planck's constant divided by the mass and the wavelength of light. Now we're going to define Planck's constant. We can easily measure the wavelength of the light. It turns out it's easy to measure the velocity of the atom, which means that you can determine the mass of the atom in kilograms. We then, by other experiments, take the ratio of the mass of this atom, it's usually something like rubidium, find the ratio of the rubidium mass to the mass of silicon atoms. That's not too hard to do either. And then we make a perfect silicon sphere. You take a perfect crystal of silicon, you make a perfect sphere. This is the most spherical object ever made on Earth. And you measure the dimensions of this sphere. And because it's a perfect crystal, you can measure using X-ray diffraction the distance between the atoms. And that means that you know how many atoms of silicon are in there. And because you know the mass of just one silicon atom, you know the mass of this object. A completely new way that's different from the electromechanical way of measuring mass, but it relies on defining Planck's constant, because that's what you need in order to get this recoil velocity. You need Planck's constant. So these two completely different ways are being used by people all over the world. Here are places where people are using both Kibble balances and silicon spheres to first measure Planck's constant, and then once we've agreed that they all are giving consistent answers, we turn that around, and instead of measuring Planck's constant, what they're measuring is, by fixing Planck's constant, they're measuring the mass of some object. And so when everyone in the world was in agreement that this was working out, this new definition was working out, they decided to fix the value of Planck's constant and felt that they had really done what the French revolutionaries had dreamed of, that they had made a system that was good for all time, for all people, something that did not rely on an artifact, something that anyone in any laboratory on Earth, or for that matter, even on another planet, could reproduce if they had the right kind of equipment and skills. And so, in a gathering in Versailles in November of 2018, the countries of the world unanimously agreed to adopt a new definition of the kilogram and the ampere, the Kelvin and the mole. And when that vote was taken, they showed this movie, which I would like to show to you now.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. Facts.
We did it. Ce l'abbiamo fatta.
We have no special.
Lo logramos.
Lei sia buoni.
我们做到了。
Biz buna nail olduk.
Proud and I.
Das wurde schon satt. Het is ons gelukt.
Vi сделали это.
Fantasella.
Vi gjorde det.
Amerika.
Mi smo to učinili. Dokázali jsme to.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shattere le lavorizia.
Selamat sukses.
Parabéns.
Ongela.
Omedetou.
Amiguida.
Onneksi olkoon.
Mabruk.
Kapai.
Aiko.
Félicitations. Congratulations.
Every time I see that movie, even now, I get a bit emotional, because 60 countries from all around the world agreed unanimously to do something good. And when I think about that, it makes me believe that possibly the countries of the world can agree on other things that will help humankind. But anyway, as a result of this, on the 20th of May, following that international gathering, on the 20th of May, 2019, the definition of mass was changed, as you've seen. But there's more. The definition of the ampere was changed. The old definition, not today, but 2 years ago, was that the ampere is the current which in two infinitely long straight wires, a meter apart, would produce a force of 2 times 10 to the minus 7 newtons per meter. You probably remember learning that in a physics class. It's no longer true. Today, the ampere is defined by defining the charge on the electron. So an ampere is a certain number of electrons per second. Once you've defined the electron in coulombs, and a coulomb is an ampere second, then that defining the charge on the electron defines the ampere. And the beauty of this is that when you've got both E and H defined, then that means that Josephson's constant, 2E over H, and von Klitzing's constant, H over E squared, are both exact, and we can use the Josephson effect and the quantum Hall effect to measure all electrical quantities in the International System of Units. But there's more. It used to be that the mole was the amount of substance that had a number of entities in it equal to the number of carbon-12 atoms in 12 grams of carbon-12. But now, it's simply a number. We've defined Avogadro's constant. And finally, we've defined the Kelvin. Redefined the Kelvin, the unit of temperature. It used to be that the Kelvin was 1 over 273.16 of the triple point of water. And today, we have defined the Kelvin by defining Boltzmann's constant. Because if you take the temperature, multiply it by Boltzmann's constant, that tells you what the energy is, the kinetic energy of the constituents of whatever it is that you're measuring the temperature of. So if you are talking about the temperature of a gas, then defining Boltzmann's constant defines what the thermal energy is of the atoms or molecules that are moving around in that gas. So it's a very atomic and very quantum way of defining what we mean by temperature. So the French Revolution brought us the metric system. Meters were the new measure of length, the measure of all things, including the kilogram, which was defined in terms of the meter using this definition of mass. The International Treaty of the Meter embodied these new definitions in artifacts, the International Prototype of the Meter and the International Prototype of the Kilogram, but gave us an international agreement about what the units would be, but still tied to this idea of artifacts. And then finally, 2 years ago, on the 20th of May, 2019, the anniversary of the signing of the International Treaty of the Meter, we had the biggest revolution since the French Revolution. And so this image that Delacroix gives us of liberty leading the people tells us that we're finally free of artifact standards and measurements, that all the base units of the SI are defined by defining a fundamental constant of nature, Planck's constant, or the speed of light, the hyperfine frequency of cesium, the charge on the electron, the Boltzmann constant, and the Avogadro constant, and so on. And it seems that we really have finally realized this revolutionary dream of having a system of measurements good for all time and for all people. Except, it seems, for time itself. Because time is still tied to a specific atom, namely cesium, rather than to a fundamental constant. So we are with time very much in a situation like we were when we had the definition of length as being based on the wavelength of light from a krypton lamp. At that time, the definition of length was tied to a specific atom, and that's what we have now. And we face the same situation as people faced then with that old definition of length based on the krypton wavelength, because there are now atoms that are better than cesium. There are atoms that can measure time 2 orders of magnitude more accurately than we can measure with cesium. And so people are developing atomic clocks using these new atoms, using higher frequencies than the microwave frequency that cesium atoms have. These are now being used throughout the world as de facto standards of frequency, as de facto standards of time. And so we face a situation very much like what we had when we needed to change the definition of length and when we needed to change the definition of mass. That is, we have a new technology that is better than the old technology, and that old technology implies and gives us a particular definition, and that definition is now obsolete. That definition is that the hyperfine frequency of cesium is about 9 point something gigahertz. And there are better ways of doing it. There are better atoms and better transitions that we could use. And so we're working on it. And what the future of time will be, I can't predict, because we're still working on what is the best new atom to redefine time. And so we come to the end of the talk, but it's not really the end because we still need to redefine the second. Thank you very much.
Thank you very much for that wonderful and very inspiring talk. I'm going to apologize to everybody because there's some background noise, but that's one of the pitfalls of having virtual events. Muchísimas gracias a todos los que nos siguen. Por favor, si tienen alguna pregunta, nos la pueden hacer por las plataformas de redes sociales de Fundación UNAM. Y puede ser en inglés o en español, ambas bienvenidas. Bill, we're going to start with some questions, well, starting backwards, actually.
Now, let me ask you, do you by any chance have two computers operating at the same time? Because the sound may be a feedback between the two computers.
No, it's a sander.
Ah, okay.
Yes. So one of the first question is, why is it that it's better to define metrics with constants than the old way?
Right. So if we define something based on a fundamental constant of nature, then it gives us something which, as far as we know, should never change. So when we had, and not only never change, but never need to be redefined. So let's look back at the definition of the meter. The problem with the original definition of the meter, based on the size of the Earth, was that it was hard to do. And so they made an artifact. The problem with the artifact was the artifact could change. It could shrink or expand with temperature, and it wasn't very easy to use either because it was a scratch. There wasn't anything fundamental about that meter. And if it was lost, you would lose all information about what a meter really was. And so people started to use the wavelength of light. The trouble with using the wavelength of a particular atom was that it wasn't the best atom. Nobody knew how to choose the best atom when they chose it because they only had limited experience and limited technology at the time. The laser had just been invented. People didn't realize how good lasers were going to be. And so when lasers got to be so wonderful, the old definition was not any good anymore, and people started to use lasers. So we had this history of constantly changing what we meant by a meter. But then that new definition, based on the speed of light, means we don't have to change again. So not only do we have something that's very good and very accurate that we can measure to, I don't know, maybe parts in 10 to the 11th or parts in 10 to the 12th, but it will never change because it's all the things that might get better, that might make us want to change the definition, are already part of the definition. So that's the key thing. That's why we want to use these fundamental constants, because we should have the very best way of doing the measurements, and it should never change. You're muted. Sorry.
Yes. So for determining the mass, are keyboard balances needed, and are measurements affected by local gravity? What happens if you were to take the balance into space?
Okay, so the answer is yes. Yes, local gravity is needed. Let me back up and answer the first question. We don't need a Kibble balance. We could do the other thing with the silicon sphere. But we can't do it in space because it relies on gravity to allow us to compare the force due to a mass due to the force due to electromagnetism. So a Kibble balance really is not going to work very well in space unless we had some way of, say, accelerating the space station to produce artificial gravity, and we could measure what that was. But now, as to the question of does it not then depend on local gravity? Yes, it does. Fortunately, we have very good ways of measuring the acceleration of gravity. The two general ways in which people measure the acceleration of gravity is either to drop a mirror and have that mirror be part of an interferometer so that you can count off wavelengths of light as the mirror falls and measure the acceleration in meters per second squared, where the meters are given by the wavelength of the light that you're using, and seconds are just given by whatever local time standard. And those ways of measuring it are better than the uncertainties in the Kibble balance. So that's good. The other way of measuring it is even more cool. You drop atoms and you measure the acceleration of atoms by measuring the Doppler shift of the transitions in the atoms, and that works even better. So it's necessary to measure the acceleration of gravity at the place where you're doing the Kibble balance measurement. Now, it's even more subtle than that, because the acceleration of gravity of the Earth is not a constant. It changes with the tides. So it changes on a daily basis. And just like the water tides at the ocean, it changes during the seasons. So depending upon the position of the sun relative to the moon, the acceleration of gravity is different. It also changes if there is subterranean water. So the level of water might change, and that will change the acceleration of gravity. So you have to make the measurement at the time you do the experiment, or you have to know how these other things change. And people have learned how to do both of those things. Now, how are people going to do things practically? They're not going to use a Kibble balance every time they want to weigh out something in kilograms. What they're going to do is they're going to calibrate platinum iridium kilograms or stainless steel kilograms or whatever are the secondary standards of mass. They're going to calibrate those against the Kibble balance, and then you use those for practical purposes. So you may ask, well, what have we gained? And what we have gained is something that will never change. You see, we used to do that using the international prototype of the kilogram as the thing to compare the working standards with. But the international prototype of the kilogram was changing. Now we have something that will never change, and that's one of the reasons why it's better.
Thank you very much. Can you tell us how are the different measurements or measures relate to each other, and how uncertainties in those measurements are determined, like distances, time, the Kelvin, and can they be measured experimentally?
Yes. Well, so the answer is everything is done experimentally, and so let me give you a little bit of an example of how they depend on each other and how we determine the uncertainties. So let's start with time. Time is the thing that we know the best. I haven't really talked about time in this talk, but maybe another time I'll give you a talk about time. But time is the thing we know best. And how do we measure its uncertainty? We make a cesium clock. So cesium is used to define what we mean by time. We make a device where we shine microwaves at cesium atoms and see what frequency is needed to make those cesium atoms change their state. And then we do things like change the temperature in the room to see if that changes things, and measure that. And then ask ourselves, how well have I controlled the temperature in my lab? How much different is that temperature from the temperature at which the cesium clock is defined, because the background radiation shifts the frequency a little bit. Or we change something else. We change the gain on the electronics or something. We see if that shifts things. And we, from that, we develop a set of uncertainties. Then we compare that cesium clock to another laboratory that has a similar cesium clock, and we look at the differences. And from combining all of that information, we come up with a value of how uncertain we are. And right now, that's a few parts in 10 to the 16. So it's incredible how good that is. Now, we need that definition of time in order to have our definition of length. Because remember, the definition of length is how far does light travel in a certain time. So we need a definition of time. The way we really use it is we measure the frequency of the light. So we have to measure the frequency of light against the frequency of cesium. And we know how to do that. But we know how to do that less well than we know how to measure the frequency of light. So there's an uncertainty that comes into the measurement of the frequency of light. But that's not the most important thing in the uncertainty in measuring length. Remember, it's based on light. Light is a wave. That means that it diffracts. So if we have a beam of light that's, say, this wide, as it propagates, it will spread out, because that's what light does. And that means that there's a little bit of curvature of the waves, and that curvature has to be taken into account. And that's the thing that limits how well you can determine length, is making all those corrections. So those are the kinds of things that come into the relationship between the constants and the way in which one determines the uncertainty. It's a lot of work, and that's what metrologists do and love.
That's quite interesting that you're linking all these measurements with light and even the work of astronomers. So can you, Tonelli Rodríguez Vasquez is saying, so from what you're saying, all of these new definitions for measurements that you described will never be improved again?
Well, we hope that they will continually be improved. In other words, take something like the Kibble balance. Every new generation of people who come and work on the Kibble balance bring to it new ideas and new perspectives, and we hope will improve its operation. I was one of the first people to be working on the Kibble balance at NIST more than 40 years ago. When I first came to NIST, I began working on the Kibble balance. We didn't call it the Kibble balance then. We called it a device to measure the absolute ampere. But the same balance has taken on a different role as time has gone on. You saw the young people in that photograph with the tattoos on their arm. They are a second generation after me that have been working on the Kibble balance, and they have made it work much better than we were able to when I was a young scientist. So when I was a young scientist working with people like Tom Olson and Ed Williams, we worked very hard, but we never did as well as these young people are doing. And I expect that the next generation of young people will improve this, so we will measure kilograms to parts in 10 to the 9 instead of a part in 10 to the 8th. And I hope that these people will start to understand what is causing these platinum kilograms to change. And maybe they can figure out what to do to fix it so that we won't have to recalibrate as often. Now, we're hoping that these new definitions will never have to be changed, that all we will do is improve the techniques that are used to realize whatever definition we have. But for time, that's not going to be the case. We're going to have to change the definition of time in order to use the new techniques. The new techniques measure optical frequencies instead of microwave frequencies. And in order to make use of that, we need to change the definition. And right now, we don't know what that change will be. I'm guessing that it will be some new atom like strontium, some particular transition in strontium. I'm guessing it's going to be the singlet triplet intercombination line, in case you're interested. But that will be able to give a new definition that works at least as well as a part in 10 to the 18, and then people will start to get better and do a part in 10 to the 19 and a part in 10 to the 20. And my colleague and friend Jun Yi tells me he sees no reason why we can't measure time to a part in 10 to the 20th. Think about that. A part in 10 to the 20th. I don't even know what that number is called.
Thank you very much. So there are a few questions regarding more of the politics about measurements. So Heiko Odabachian is asking, does the ability to determine a universal measurement system translate into political power of some sort?
Well, okay. In the past, you might have thought, and I think it was true to some extent, that the countries that had access to the artifacts, the primary standards, had some greater, at least, power to do certain kinds of measurements than did countries who didn't have access. So, for example, if you were one of the signers of the Convention de Mètre, you had the right to compare every few decades your mass standards. First of all, you had the right to have a mass standard manufactured by the International Bureau of Weights and Measures, and to compare that to the international prototype of the kilogram. People who had not signed that treaty and who had not paid the money that you had to pay to support the International Bureau of Weights and Measures would not have that kind of access and would have to rely on somebody else calibrating their standards. So there might be a certain power imbalance. Today, there's no such thing. Anyone who has the skill can do it, but it still requires a lot of money. You see, in the past, it may have been that some countries didn't want to spend the money to become members of the international community that is governed by the International Conference on Weights and Measures, and that today that they're not going to be in any better shape because it takes money to build a kibble balance. It takes money to make a perfect silicon sphere, but anyone can do it. They don't have to rely on some international bureau to provide these standards. Now, this sometimes makes the International Bureau of Weights and Measures a little bit fearful because they feel that maybe their usefulness is no longer evident because nobody is required to come to them. But they are still the premier laboratory that is figuring out all of the difficulties. And they are the ones who still gather together the world's metrology community in order to make decisions about, for example, what the new definition of the second will be. So my opinion is that the International Bureau of Weights and Measures will be as relevant to metrology as it ever has been, because we still need an international community to make this work as well as it should.
Thank you very much. So can you tell us a little bit about how is it that the old metric standards were shared with among countries, those that had the standards, the artifacts, with those that didn't, and how does it happen now that even though there's a definition, not every country has the equipment and the expertise to make their own measurements?
Right. Well, first of all, I should say that the details of how this is done is something that I'm not really an expert in. There are international groups of people. For example, for the Western Hemisphere, there is a a working group of metrologists that share information throughout North and South America to be sure that these kinds of standards are shared internationally. But to go back into history, if I'm remembering correctly, 17 countries from around the world agreed in 1875 to meet in Paris and to sign this treaty. Part of that agreement was that they would pay money to the new International Bureau of Weights and Measures. And some of that money went in not only to making new standards, but to making copies of those standards that were given to all of those countries. So as a result of signing that treaty and paying the money to support the new international community, all of those signers got a copy of the kilogram and of the meter, and then used that as their national standards. By the way, the United States has been using those standards since shortly after 1875 to maintain its standards of measurement. We are not legally using inches. We define what an inch is in terms of a meter. We do not have inch standards anywhere. We do not have pound standards. I mean, we have them, but they're not useful anymore. We define those things in terms of the international system of units. And every other country that signs the treaty does that. So that's how those international standards work, or worked back when we had artifacts, is that everybody who was a signer of the treaty and paid their dues, so to speak, to the international community, had access to these international comparisons. Then you have regional groups that do comparisons, and in this way you can ensure that everybody has a connection to the fundamental definitions. Maybe not at a part in 10 to the 8th. Maybe their standards will only be reliable at a part in 10 to the 7th. But let's face it, most people don't need to know what a mass is to a part in 10 to the 8th. Only the people who are working at the very cutting edge of metrology need to know that, and so it works out. Now, maybe Jaime knows a little bit more about that, because, of course, you in your positions have had to deal with a lot of international issues. Would you like to say something more?
Well, not now. I think we can do it later. But yes, I think in the everyday life we don't really need this kind of precision, but it's important for a lot of applications, including, for instance, the geopositioning system, which we use every day. We really need this high precision. I can comment later. Thanks.
Okay.
So I think you both have partly answered the next question, which is actually going back to time. And that is, why is it that we need high precision when measuring time?
Right. So that's right. Jaime has told us that the global positioning system has put a lot of demand on the quality of time. So we need to have atomic clocks that keep extremely good time, in the sense that they don't change, that they don't drift, and that's what atomic clocks give us. If it weren't for that, and the ability to have those clocks not only on the ground but in space, we wouldn't have a working global positioning system. But it's more than that. On the Earth, people need to synchronize communications. There are certain kinds of synchronous communication where people at both ends, both the sender and the receiver, need to know what time it is, so that a particular part of a message can be routed to a particular receiver. And so one of the ways in which you can do that is to have atomic clocks on both ends to allow you to do synchronous work. Now, most communications are done asynchronously, but there are some communications, especially ones that need to be very secure, that are done synchronously. We also need atomic clocks for doing certain kinds of radio astronomy. You need to have an interference between the radio signals received at one radio telescope with the ones received at another radio telescope. And one of the ways in which you do that is you record the radio signals at the same time that you record the time that they were received using an atomic clock in both locations, and then you can combine the signals later. So it's another one that's a very scientific, fundamentally scientific use of atomic clocks is it possible that these constants of nature that we've been talking about are not, in fact, constant? Now, in the case of something like the speed of light, it doesn't even make sense to ask that question because, of course, it's constant because we've fixed it by fixing the definition of the meter. But if you take something like the fine structure constant, which gives us a dimensionless measure of how strong the electromagnetic force is, that's a number that in principle could change with time because it doesn't have any units. And so if we have two atomic clocks whose frequencies depend upon the fine structure constant in different ways, we can compare them and see whether the fine structure constant is changing. All we have to do is have the two clocks in the same laboratory, measure the ratio of the two frequencies, and see whether it changes with time. And people are doing that. And so far, no change. But they're being able to make this measurement better than anyone has ever made such measurements before. So these are some of the reasons why we need time to be so good.
Thank you very much. We have a question about the Planck constant. Is it a measure of dimension? And is it the smallest measurement of dimension there is?
Okay, so it depends on what one means by dimension. The Planck constant has dimensions in the sense that it has units. It has units of energy times time. One of the ways I like to think of its dimensions is joules per hertz. Because if I multiply it by a frequency, it tells me what the energy is in joules of a photon having that frequency in hertz. If you mean dimension in terms of length, it doesn't have the units of length. It has the units of dimension of what's known as phase space. So phase space is the product of spatial dimensions and momentum. And Planck's constant has that unit. So it has units of meters times momentum. And so we often think about phase space. We do this in quantum mechanics a lot, is think about phase space and think that phase space is quantized in units of Planck's constant. So that is, it's not that space is necessarily quantized that way. It's that it's a convenient scale on which to think about things going on in phase space. So an example of that would be, let's say I get a bunch of atoms together, and let's say that I keep increasing the density of the atoms in phase space. That means I want more atoms in real space, and I want to have a smaller spread of momentum of the atoms. That means that the density in phase space is increasing. When those atoms get to have a density in phase space of 1 atom per cubic H, then they become what we call quantum degenerate. And so that's an example of how Planck's constant comes in as an important dimension, but it's dimension in phase space, not in regular space.
Thank you very much. I think I'd like to change tack a little bit. And you are one of the few people in the world who have been awarded the Nobel Prize. So you were awarded the Nobel Prize in Physics in 1997. Can you, and it is for something that it was slightly different to what you've been talking to us today. So could you briefly tell us what it is that you were awarded the Nobel Prize for?
Okay, sure. Well, first of all, as I hope you'll see in a moment, it's not completely separate from what I've been talking about today. But why did I talk about what I'm talking today? Because when I first went to NIST, that was my job, was to do the things that led to what I've talked about today. But at the same time, I was working on something else that's very important to NIST. And the thing that I was working on is called laser cooling. So what is laser cooling? Laser cooling is something that sounds completely crazy. We take a gas of atoms, we shine light on it, and we make the gas cold. Now, normally, if you shine light on something, you make it hot. But we didn't come up with the idea, but other people came up with this idea, and we figured out how to put it into practice. That was what my group was doing, was figuring out how to put into practice this crazy idea of shining light on something and making it cold. How does it work? Well, you may remember from the talk that I mentioned that light, photons, carry momentum. That means they can push on things. And in that example that I gave, the light was giving a kick to an atom, and we measured what that kick was. So imagine I've got an atom coming along like this in a gas, moving at a velocity that's usually pretty fast, a few hundred meters per second. And I have light beam coming this way. Every time the atom absorbs a particle of light, it'll get a kick in the opposite direction. And eventually, if I give it enough kicks, it'll slow down, and it won't be moving at 100 meters a second. It may be moving at a few millimeters per second. That's what we hoped for. And that's what we did. We learned how to do all kinds of tricks to make a gas of atoms, so the atoms in that gas were moving at velocities that are on the order of millimeters per second instead of hundreds of meters per second. Now, why was that interesting to NIST, to the metrology laboratory? Because atomic clocks are limited in how accurate they can be by the motion of the atoms themselves. So, in a certain sense, the atoms are ticking at the frequency that we use when we define a frequency in that atom. The atom is, in a sense, ticking at that frequency. But measuring that ticking frequency is hard to do when the atom is moving at the speed of sound. When we make the atom move a lot more slowly, at only a few millimeters per second, then we can make a much better measurement. And so laser cooling has allowed us to go from atomic clocks that were good to a part in 10 to the 14 to atomic clocks that were good to a part in 10 to the 16 for cesium clocks, and now atomic clocks that are a part in 10 to the 18 for optical frequency clocks, but those clocks are laser cooled as well. So the part in 10 to the 16 atomic clocks are laser cooled, and the cesium clocks and the part in 10 to the 18 optical clocks, which will become the next generation of atomic clocks, they are also laser cooled. So that's been the big application of laser cooling, is to make better atomic clocks. But today we're using them to do all kinds of other things. We're using them for quantum information. We're using them for quantum simulation, for studying the behavior of unphysical Hamiltonians. I mean, things that are very basic science are being applied in cold atomic gases. So it's been a lot different from what we imagined we would be doing with these things when we first started.
I think that's a very important point that you're making, that often when people think about experiments or new studies, you don't really understand or grasp its full potential. And I guess that's the importance of supporting both basic and applied science.
Absolutely. That's a wonderful insight. And in fact, leads me to say one more thing. We didn't imagine all the good things laser cooling would do for us when we first started. We also didn't imagine how well laser cooling was going to work. We had a theory of how laser cooling should work, and it turned out it was all wrong. It works much better than what that theory said. The theory isn't really wrong. It's just that there's something else that happens that we had no idea about that makes laser cooling work even better than we imagined. So not only were the applications much more than what we imagined, but the whole process itself worked better than what we imagined. And we wouldn't have learned any of those things unless we had taken a basic research perspective on this work. But we might not have even gotten started had we not taken an applied research perspective on it. So you need both, just as you say.
Yeah, thank you. So can you share with us when and where were you when you found out that you were getting the prize? What did you feel?
Right. Well, so I should explain a little bit. The prize is awarded by the Swedish Academy of Sciences. So they are in Sweden, and I live near Washington, D.C., on the east coast of the United States. But at the time that the prize was announced, I was attending a meeting in California on the west coast of the United States, which is 3 time zones earlier. Now, the prize is generally announced around noon in Stockholm. And their custom is that about at the same time that they announce it publicly, they make a telephone call to the recipient to inform the recipient. So that would have been 6 o'clock in the morning if I had been in my home, but I wasn't. So I got a call at about 3 o'clock in the morning in California. Now think about this for a moment. They knew where I was. It took hours before the journalists figured out where I was and started to ask me questions, as journalists do. But the Nobel people knew where I was, knew what hotel I was staying in California at 3 o'clock in the morning and called me up. Now, I should also say that the day before, a number of us were sitting around at the end of the day of the conference. We'd gone to all of the conference programs. It was an exciting program, and we were sitting down having some tea or some coffee and talking about the fact that tomorrow they were going to announce the Nobel Prize. And we were saying, wouldn't it be wonderful if the people who have just recently gotten Bose-Einstein condensation, this was an application of laser cooling, and wonderful, and it's one of the biggest fields of research in physics today, Bose-Einstein condensation and quantum degenerate gases. Wouldn't it be wonderful if they got the Nobel Prize? Because some of those people are actually attending this conference, and this would be really great to have a press conference, and they would be there and talk about their work. It would just be fantastic. Nobody said, maybe you're going to get the prize, Bill. So it came as a really big surprise to me to get a call at 3 o'clock in the morning telling me that I had been selected to receive, along with Claude Cohen-Tanuji and Steve Chu, the 1997 prize. Now, here's another point. After the person who called me was the head of the Royal Swedish Academy of Sciences, who was somebody who works in, I think, genetics. So maybe you might even know who it is, but I don't even remember the name. Not somebody I knew and not somebody I know now. telling me that I've received the Nobel Prize. As soon as he was finished telling me that, he said, here is somebody who wants to congratulate you. And he gave the telephone to somebody who I knew personally, who was part of the Nobel Committee, to congratulate me. Now, I think the reason he did that was because sometimes people have played a very nasty joke on people and called them up and used a fake Swedish accent to say that they won the Nobel Prize. And they wanted to make sure that I realized that this was not a joke. And so I talked to somebody whom I knew personally. And that was very nice as well, because, you know, we'd known each other for some years, and it was very nice to talk to somebody who, whom I knew about such a wonderful occurrence. So that's my story of the Nobel Prize announcement.
Wow. Okay. So I guess you didn't have a very good night's sleep after that, right? So.
No. They told me that we're sorry. They realized it was 3:00 in the morning. They said, we're sorry, you're not going to get any more sleep because we're announcing this publicly. And of course, the press will be all over you. The press did not find me for several hours. We did have a press conference, as we had imagined, but it wasn't the one we thought we were going to have. But I did not get any more sleep. I started trying to call my wife. Yeah.
Well, thank you. Thank you very much for sharing that story with us. So I want to conclude with one last question. There are many young people right now, women and men, who are starting to think and consider whether to pursue a career in science. What would you tell to them? A tip that you wish someone had told you when you were starting?
Okay, well, first of all, I would say that I can't think of anything more exciting to do with your life than to have a career in science. One of the things that a research scientist experiences is we learn something new almost every day. And a lot of the time, it's something new that no one else has ever learned. Now, sometimes it's not things that change the world, but sometimes it's things that are pretty important and change things a lot. To be in that kind of an adventure where you're learning new things all the time is just amazing. Of course, there are other careers that can be similarly satisfying, but if you already have that innate curiosity, if you haven't lost your childlike wonder about what the world is like, your childlike curiosity of wanting to understand why things happen the way they do, then science is just such an amazing career for somebody like that. So part of my advice is, if you want to go into science, don't ever lose your curiosity. But another thing that we were talking about before we started that I didn't understand about science, when you become part of this adventure of scientific research, you become part of an international community of people who are both cooperating and competing in a friendly way to learn more about the way this wonderful world that we live in works. And so, as a scientist, you have friends all over the world. And this is just a wonderful thing. So, Jaime, we met for the first time in Lindau, if I'm remembering correctly. And since then, we've met any number of times in Mexico, and I'm sure we will meet in other places as well. And this is because we are scientists, that we have these kinds of connections. And it's not something I realized when I was a student would be one of the benefits of science, is that we would have these kinds of international connections.
Thank you very much. When I was young once, and I was thinking about whether to pursue science as a career. I made a list a little bit similar to Darwin's list, whether he would marry or not. And the one thing I had pro science was you get to travel a lot.
And you knew that because your father is a scientist.
Yeah. Well, thank you very much, Bill. I think you've been very generous with your time, and I now have a good excuse when I say just a second, and that second extends, and that is that we yet not have a constant to measure it. So I know what to say from now on. I'm gonna pass forward to Dr. Urrutia to close the session.
Muchas gracias. Thanks very much. It's great listening to you, and congratulations for your studies and research. It's very interesting, and thanks for sharing your enthusiasm and passion for science. The last comments illustrate how science works, how scientific questions are being put forward, and how you need to move on, and what made new discoveries. I think it's great hearing how you consider science. And I was also thinking about one of the questions and the importance of having this new system and having these high precisions. And this is, of course, particularly important for science and scientific experiments, but it is also important for our everyday life. When the laser was developed, I think nobody knew what the applications will be and what the importance. We have the laser everywhere in the supermarket. It's our best way to measure distances and so on. So these new discoveries at this incredible precision we now have in the future, and perhaps in the very near future, will represent our new technological, our new tools. And having this precision for measuring a distance, mass, time, and electric current will certainly will translate into, for instance, our tool to detect the gravitational waves depends on the accuracy we have to measure distance between the detectors and time. And it's interesting how everything is interconnected. And with this new detector system for gravitational waves, we will use the movement of the planet around the sun to do the measurement. So we will be measuring long distances far beyond our own planet. So thanks very much, and we also very much appreciate your friendship and generosity, particularly for our students and young researchers. And in this Lindau Nobel Prize meeting, the group of Mexican young researchers were really fascinated with your work, and also by the way you interacted with them, you approached them. We have a wonderful dinner with you and a lot of interesting conversations. And we look forward for meeting you again in Mexico in the very near future. Pues muchas gracias. Felicitamos al doctor William Phillips felicitamos al doctor William Phillips por la conferencia y por su trabajo de investigación y por la generosidad y la amistad. Y la parte que hace interesante su trabajo es pues la pasión, el entusiasmo que se le pone. Y esto yo creo que es pues la clave del éxito. Y cuando uno hace algo con el gusto de hacerlo, yo creo que cuando salen mejor las cosas. El doctor Phillips es miembro de la academia y participa en muchas de nuestras conferencias y actividades con los estudiantes, con los profesores, con la colaboración de proyectos. Entonces realmente es muy importante. Le agradecemos mucho entonces al doctor Phillips, agradecemos al Consorcio de Universidades por la Ciencia y aprovecho también para invitarles el próximo martes. Tenemos una conferencia por una joven investigadora que recibe también el premio de la Academia de Mexicana de Ciencias, la doctora Mildred Quintana, que le presenta esta nueva generación que tenemos de científicos en el país. I take the opportunity to invite you for the next conference, next Tuesday at the same time, by a young researcher, Mildred Quintana from San Luis Potosí, where we also have a very talented young researcher, Eduardo Gomez, who was a student with Professor Phillips. And Mildred represents this new generation of talents we have. So it's a pleasure to invite you. Muchísimas gracias. Y reiteramos pues que este ciclo de conferencias es parte de esta colaboración internacional muy amplia con universidades en el país, en Estados Unidos, en Inglaterra, en España, Brasil. Es una de las prioridades de Fundación UNAM en adición a los numerosos programas de becas. Le voy a pasar la palabra a nuestro presidente de Fundación UNAM, el licenciado Dionisio Meade. Thanks very much, Araxi. Thanks, Demetrio. Thanks, everyone. And I will invite our president of the UNAM Foundation, Dionisio Meade, to say a few words. Thanks very much again.
Thank you very much. It was a pleasure. And I just want to make a small comment. It's very, particularly William Phillips, he has the particularity to explain in a very easy way very complex problems. But it was very easy to follow the talk. And I have a number of comments of some students and colleagues, and they have the same impression. It was an incredible talk, and very easy to follow. As I said, explain these ideas in a very easy way is a very difficult task. And well, thank you very much for the conference. It was my pleasure.
A pleasure for me as well.
Muchas gracias de nuevo. Ha sido pues una gran conferencia. Hemos aprendido mucho, sobre todo los que no somos expertos en ciencias. El metro ya no es lo que era, el litro ya no es lo que era, un kilo ya no es lo que era, y nos ubica pues en el formidable mundo de la ciencia que hoy se nos presenta nuevamente. El tiempo y el espacio que hoy nos han permitido a cada uno estar presentes en esta plática sigue siendo para cada quien un gran misterio. pero es un misterio al que nuestros jóvenes están convocados a sumarse, a investigar si se suman a este mundo de la ciencia, a este mundo de la investigación que William nos ha descrito de manera fascinante. ¿Por qué vale la pena entrar a este mundo? La nueva realidad es una búsqueda permanente del conocimiento y la nueva realidad demanda, como aquí se ha visto, el respeto a la ciencia, que hoy es un imperativo. La conferencia del Dr. Phillips acredita el avance de la ciencia que se da día a día, aún en temas que parecían ya resueltos. Por eso hay que estar abiertos al conocimiento. Ojalá esta plática de William Phillips convoque a nuestros jóvenes a entrar en este fascinante mundo, a este mundo fascinante de valores y de conocimiento. El doctor Phillips también tuvo un día, su primer día de clases. El doctor Phillips un día también hizo su primera investigación y con ese trabajo duro, un día recibió ese telefonazo a las 3 de la mañana que acreditó que se había ganado el premio Nobel. Gracias por compartir esa experiencia. Gracias por suscitar esta inquietud de preguntar, de ser como niños. Ese deseo de saber lo llevó al premio Nobel. Quizá entre nuestros escuchas haya alguien que en el futuro pueda obtener también un premio Nobel. Yo estoy seguro de que nada le daría más gusto al doctor Phillips que a alguno de los que estén escuchándolos, siguiendo esta sed de investigación, esta curiosidad de saber, se genere también la obtención de un premio Nobel. Gracias por compartir y gracias por sembrar estas semillas de concordia, de compartir y de competir. Ahí está la esencia del saber. Ese es el propósito de nuestra universidad. Ese es el propósito del consorcio y es lo que ha animado a seguir adelante en este esfuerzo. Gracias a todos. Ha sido una gran presentación y seguimos contando con ustedes en el futuro, que seguimos contando que seguirá formando a muchos científicos mexicanos y que el mundo se verá beneficiado de esta posibilidad de más y mejor conocimiento. Gracias a todos y seguimos con entusiasmo estas pláticas que el consorcio nos ofrece martes a martes.
Thank you very So, but it has been a true pleasure to be with you, and I thank you for all of your comments and your questions. It's been a wonderful experience. Thank you very much.
En Fundación UNAM seguimos trabajando por la cultura, la ciencia y la educación. Sin salir de casa, reflexionarás con los martes de ciencia a través de las conferencias Universidades por la Ciencia, que emitimos en conjunto con el Colegio Nacional. Y para disfrutar, regresamos con la segunda edición de los ciclos de documentales de Jueves de Ciencia, con la transmisión especial de TV UNAM. Además, conversamos sobre nuestra nueva realidad y sus afectaciones en distintas disciplinas a través del Corredor Cultural de Autonomía. Sigue nuestras redes sociales y no te pierdas ningún detalle en www.fundacionunam.org.mx.
Se han efectuado varias estimaciones de cuántos hongos existen en la naturaleza, y es un dato difícil de precisar. Se ha calculado 1.500.000 especies, de las cuales conocemos hasta ahora alrededor de 90.000. Ni animales ni vegetales, los hongos son tan excepcionales que pertenecen a un reino diferente.
you.